Hello everybody, good to see you. How are you? And welcome back to Ask Math Anything. Sorry we started a little bit late. I was getting a few things ready. Now, if you've never been here before, what we're going to do is we're going to talk about math, but we're going to have all kinds of random questions that people ask. And if you do have any questions yourself, please feel free to ask whatever you might be thinking about. Now, at the same time, if you've been here before, you know that we'll always be talking about questions which I hope can be explained in terms of algebra and geometry. And unfortunately, sometimes my hope is wrong, in the sense that it might end up being maybe a bit too difficult or a bit too easy. But that's actually what happens whenever you do a live stream like this. You never know quite what you're going to get. So let's see. I wonder if we can find some interesting problems to all think about today. If anybody has any math questions, please feel free to ask. I also see that it's Canada Day. Happy Canada Day. I guess we have some people here from Canada. Welcome. Okay, what do we have here? Oh, this is a good question. So this is a question by Daksh Gupta. I have a bag that has some green and yellow coins. So there are some green coins and some yellow coins. A green coin is worth 5 bananas. And a yellow coin is worth 7 bananas. And the question is, what's the largest number of bananas that this bag of coins cannot be worth? Oops. That a bag of coins can't be worth. How would you do these kinds of questions? So now, at first it might seem, well, are you sure you can always make things with bananas? For example, if I wanted to have 3 bananas, it wouldn't work. You couldn't do it with green or yellow coins. That's obvious. I also couldn't do it with 6 coins. Sorry, I couldn't do 6 bananas either. And indeed, some people said this is called the Frobenius McNugget problem. And that's because this could also be called the chicken coin problem. You see, there are some names for this theorem. We're about to use a theorem. The theorem is often called the chicken McNugget theorem. Or it's called the Frobenius coin problem. And it appears that some people in this live stream have decided to call it the Frobenius McNugget problem. And I'll say, if you'd like to call it the Frobenius McNugget problem, you could just as well call it the chicken coin problem, or maybe the banana coin problem, or the coin banana problem, however you like. But there is actually a nice way to figure this out. In fact, actually proving this is quite difficult. Maybe I shouldn't say it's quite difficult. It's just something we do in our number theory course, but it takes a while to work up to. But there's a really neat formula. Actually, I think all you have to do is to do something like 5 times 7. Let's try to find out, okay? I think the answer is something like 5 times 7. Except it's not 5 times 7, because obviously I can make 35 bananas, right? I can do that. I believe you have to either add or subtract something. Well, you know what? Let's actually work it out. I don't remember the answer. So here's how I'll actually figure out how to do it. Alright? So I can do certain things with 5, but I have things that are worth 5 bananas and things that are worth 7 bananas. Here's what I can do. Suppose I use, let's say, use 7 banana coins. Then what I can get with using only 5 banana coins is I can get 0 bananas, I can get 5 bananas, I can get 10 bananas, I can get 15 bananas, I can get 20 bananas, I can get 25 bananas, I can get 30 bananas. These are all the things I can get without using any 7 banana coins. Now what if I get one 7 banana coin? What if I use 1 7 banana coin. Then I could get 1 7 banana coin and 0 5 banana coins starts at 7. And then 7 plus 5 is 12. 12 plus 5 is 17. Oh, it's easy to add. Adding 5 is fun. 27, 32, 37, and so on. The important thing I want you to see here is that there's a nice pattern. The nice pattern is, from the 0, using none of the 7 banana coins, I can get all these multiples of 5. Now here I get what are called multiples of 5 with remainder 2. Right? Here I get multiples of 5 with remainder 2 starting from 7. So let's keep track of what is the remainder. Remainder, we call it remainder mod 5. So remainder mod 5, all of these are 0, all of these are 2, because 7 leaves a remainder of 2 when I divide by 5. Now let's keep going. Suppose I use 2 7 banana coins. Use 2 7 banana coins. Now you start from 14 and 0 5 banana coins, plus 5 bananas, plus 5 bananas, plus 5 bananas, plus 5 bananas, and so on. And this, the remainder when I divide this by 5 is 4. Wow, maybe I should use this pinkish purple color. 4. Next, let's keep going. Suppose I use 3 7 banana coins. Then I start from 21. And then 21 plus 5 is 26, 31, 36, 41, and so on. And what are all these remainders when I divide by 5? All these remainders are 1. Let's try using 4. And I promise you this is going to be worth it. Look at what happens. If I use 4 7 banana coins, then I get 28 bananas, or 28 plus 5, which is 33 bananas, or 38 bananas, or 43 bananas, and so on. And these all leave a remainder of 3 when I divide by 5. But now, why did I do this? What happens if I try to use 5 7 banana coins? If I use 5 7 banana coins, I can get 35. Oh, wait, but this 35 was also here. Do you see that? I don't get anything new. What I've just showed here is that if I'm going to try to use 5 7 banana coins, it's not like I get any new things at all, right? I'll just get a certain number of bananas, which I could get before, and 40 is also there. And in fact, we've just explained how to do this chicken McNugget problem. If you look at what's going on, I can go and see here are all of these different numbers of bananas I could get. And if I have any other thing, like using 6 coins with 7 bananas each, that gives you a 42. And the 42 is just what you'd have there. It just continues from there. So what that means is all of this stuff adds nothing new. So who cares? All of these things down here is nothing new. Now that we know that all of these add nothing new, I just look here and I say, what's the biggest number that's not in this list? Can anyone tell me? Well, I have a big list. How would I know what's the biggest number not in any of these lists up here? What do you think? Is it 53? Is it 33? Well, is 33 in this list somewhere? 33 is in this list here. What's the biggest number not in this list? I have all the multiples of 5, starting with 0. Okay, I have all of the things that have remainder 2 when I divide by 5, starting with 7. The way you should think of this is what's missing. What is the biggest one that's missing from each of these remainders? You see, this second row is missing a 2. So there's a 2 missing. And the next row, the third row, is missing a 9, right? And the next row is missing 16. Of course, it's also missing an 11, it's also missing a 6, but it's missing a 16 here. And then this row here, this row is missing a 23. And so the 23 is the biggest missing number. I see a lot of people here have said 23. 23 is the biggest missing number because, you know, if I looked at all of these rows, I'm missing either a 2 or things which are up to a 9 or things which are up to a 16 or things which are up to a 23. So the answer is 23. Okay? So the answer to this whole question is 23. Now, is there a formula for this? Actually, there is. So the formula for the 23 has something to do with multiplying 7 times 5. And then you subtract 7 or 5 or something. And the way I think of this is, let's look at how I got that 23. The 23 came from 7 times 4, and then I minused a 7. I did 7 times 4, and then I minused a 5. That's how I did it. I was curious about if I have coins which are worth 5 and coins which are worth 7, and the biggest number that I couldn't get was 7 times 4 minus 5. Okay? So somehow the answer is 7 times 4 minus 5. How could I turn that into a formula? Well, what's the 4 from? The 4 came from trying to go over all of the different remainders. And of course there are 5 different remainders. So the 4 is actually 5 minus 1. Okay? So what's actually going on here is that this is actually 7, let's write it this way, 7 times 5 minus 1 and then minus 5. Now some people prefer to write this formula as 7 times 5 minus 7 minus 5. And that is indeed the answer. Whenever I have this Frobenius coin problem, or this chicken McNugget problem, or the chicken coin problem, or the Frobenius McNugget problem, whatever you want to call it, the answer is just 7 times, like the product of the two things, minus 1 minus the other. There! Now you can memorize it! Yes, but you see, I was afraid. I forgot, I didn't remember, is it minus 7 minus 5, or is it plus 7 plus 5? I actually forgot the answer. And so, since I forgot the answer, the easiest thing to do was just to derive it. So now let's practice. Let's try a Frobenius McNugget problem like this. Suppose that you have coins worth, I don't know, how about $14? Whoa, those are really expensive coins. Let's use cents, okay? Not $14. 14 cents and 91 cents. What is the biggest amount of money you can't make? Well, there's a formula, right? So we just use this formula. How hard can this be? The formula just says we take 14 times 91 minus 14 minus 91. How many people like this answer? Seems reasonable. That's what formulas are good for. We memorize formulas, right? And then we just plug them in. It looks like some people know that this won't work. So the thing here, the way I say it, it's coming, right? So the thing is that somehow the answer is, don't just use a formula. The answer is actually, there are lots of numbers you can't make. The reason there are lots of numbers you can't make is that 14 is 7 times 2, and 91 is not a prime. 91 is this very annoying number that looks prime, but it's not. Okay? So the problem is that the 91, anyone know the prime factorization of 91? Could you please tell us? What's the prime factorization of 91? Yes, 7 times 13. And the 14 is 7 times 2. So guess what? If you use these coins, no matter how many coins you use, the answer is always going to be a multiple of what? What do you think? If I use some combination of these two coins, since one of them is worth 7 times 2 and one's worth 7 times 13, no matter what, your answer is going to be a multiple of 7. So here's an amount of money you can't make. Here's an amount you can't make, 701. Of course you can't make 701, because 701 is not divisible by 7. 700 is divisible by 7. Or here's another amount of money you can't make, 7,000,000,001. Because 7 billion is a multiple of 7, plus the 1, you have no way to get it. Oh no, in fact, even 7 Google and 1, you can't make. So what this shows is that this answer, this question actually has no good answer. The answer to what's the biggest amount of money you can make is not this, but the correct answer is there is no biggest. because it's unbounded. It's like there are big numbers. It's not really quite infinity. Infinity is not a number, so that's why I'm saying the answer is no biggest. You can get as big as you want. All right. More questions. Yes. Alan Tang. How do you find the square root of a nuclear missile launch speed? I need to know by Friday. You have some very interesting homework assignments. I don't quite know, but I'm going to say it probably depends on what kind of nuclear missile, because assuming that the speeds, maybe you want to get it into full orbit or not quite to orbit, or I don't know. So I'll say the answer is it depends on the kind of nuclear missile that you're trying to launch. Hopefully your teacher gave you more details. P14Y3R0N3 asked, does the formula still work for more than two numbers? You know, like what if you had three kinds of chicken McNuggets? Then like three different sizes or three different kinds of coins, then what's the formula? My understanding is that actually there's not a nice formula for three. And that's why you don't learn this. It's like it becomes messy. The reason it becomes messy is because then there's all different ways to combine and get different remainders. That's related to something called the Chinese remainder theorem. And Dakshgupta said that's an unsolved problem. So it's a funny thing, like for the two different kinds of coins, boom, there's a nice formula, unless there's a common factor. Okay, that's the complete answer for 2. But for 3, nobody knows. And so that's a really, really interesting question. It's funny how in math you can go from something easy to something really hard just by making one little change. Jiang Michael, that looks interesting. You want to know the least odd prime factor of some number. But the number looks awful. 2019 to the power 8 plus 1. Uh-oh. You want the least odd prime factor. Why couldn't you have asked me for the least prime factor? I can tell you the least prime factor. That's easy. So the least prime factor is just going to be 2, right? That's easy. The least prime factor is 2. But now if I want the least, if I want to have the least non-even prime factor, what could we do here? Well, let's look at it and stare for a little bit. What? You gave me a question number 13 on the 2019 Amy? In that case, what I'm going to say is let's put this one off. The only reason is because I made a promise to people that we wouldn't go way too deep. And yes, I agree it was made in 2019. But if it's an Amy problem number 13 or number 14, this is something that could easily take us a significant amount of time. And also, it might be a bit too hard for some of our audience. It does look like a really neat question, though. Okay, so neat. Let's leave this for people if they're curious about this. They can play with this after, but we don't want to go too far afield on this live stream. The answer is probably not going to be something simple like 5. It's probably something serious. I see that Alexander Chung has asked, can we explain why 0.999999 repeating equals 1? We actually did that on an earlier live stream, but the basic idea is that whenever you write the ... that's just secret code. Sorry, not secret code. That's the way mathematicians express. That means whatever the number gets closer and closer to, if it gets closer and closer to something. And if you look at the 0.999999s and you stop anywhere, the difference between that and 1 is something for which that difference, which is 0.00001, gets closer and closer to 0. Actually, it converges to 0 as you add more digits. So that's actually why it's equal to 1. Okay. A geometry problem. We haven't done these in a while. So let's see. What's this one? This one is from Lakshmi Priyanka. Lakshmi Priyanka says, I have a right triangle, ABC, with hypotenuse AC. So let's try to draw this. ABC is a right triangle with hypotenuse AC. Okay, suppose that AB equals 5. Suppose that AC equals 10. And suppose that D is the point where the bisector of angle A intersects side BC. Something tells me this is not really drawn to scale. If that was 5 and that's 10, that looks a little bit crazy. I don't believe it. I'm actually going to just change the letters a little bit, because that will give me something which I can imagine is drawn to scale. We'll flip the A and the C. Now that looks sort of believable. That's like 5, that's like 10. And now what we're going to do is we're going to draw the bisector of angle A. And then we're going to go over to side BC, and that would be D. So D is here. And what are we supposed to do? What is the length of AD? Oh. Okay. So this is a geometry question. And I'm glad that you like the straight line. I did my best. So if I need to go and find this part out, let's start by using some geometry. So if I have a 10 and a 5, oh, that's a very special kind of right triangle, by the way. Do you know what kind of right triangles have this hypotenuse to be exactly twice one of the legs? That's a really special one. That's called a 30, 60, 90 right triangle, because if I draw you an equilateral triangle, if I drew an equilateral triangle like this, pretend it's equilateral, then if I take this line and I cut over to here and cut it in half, well, it cuts it in half, right? So whatever this was, if that's x, this is x over 2. And that would be a 60-degree angle. Okay, so this is now really nice, because that means that the big angle is 60 degrees. This one cut it in half. If it cut it in half, then each one is 30. But now I can do this much easier. It looks like a Dorito. Yes, it does. So now if I have a 30-degree angle, obviously not drawn to scale, if I have a 30-degree angle and that's a 5, what's this one? Well, the relationship in the 30, 60, 90 is that whatever this is, it multiplies by square root of 3 to make that thing. A 30, 60, 90 right triangle is like 2, 1, square root 3, right? That's the way that always happens. So in the 30, 60, 90 right triangle, if it was actually drawn to scale, 60, 30, it would be something like 2 and 1 and square root of 3. And that's by the Pythagorean theorem. So now, once I know that, oh, how do you remember that? How do I remember that it's 2, 1, square root of 3? Here's how. I know that this thing came from an equilateral triangle. So that would be like a 2. This would be like half of it, which is 1. Much nicer than saying this is a 1 and this is a half. Who likes fractions? Not me. So let's call this one a 2, let's call this one a 1. And then if you use the Pythagorean theorem tells you that this guy is the square root of this squared minus this squared. So it's the square root of 4 minus 1, which is the square root of 3. So that's the ratio. Now we go over here. If that's 5, then this is 5 root 3, right? Oh no, it's 5 over root 3. It's 5 over root 3 because I'm going from the long side to the shorter side, okay? So this piece is 5 over root 3. And then if I want to go from here to the question mark, I times 2, right? So then this thing has to be times 2 because the ratio between this short leg and the hypotenuse is times 2. So this question mark is 10 over root 3. Now, the only catch here is that sometimes people don't like if you write the answer this way. Do you know why? It's because it's really hard to calculate that. How would you calculate that? Suppose somebody told you, figure out what is 10 divided by root 3. Well, it's not that hard, right? Just divide. Watch. Watch me divide 10 divided by root 3. 10 divided by root 3. Oh, first I need to know what was root 3. Well, let's go ahead and start. I have 10.0000, bunch of O's, divided by root 3. Anyone know what is root 3? Well, it starts with 1.732, and there's more stuff. Who wants to do this? Nobody. I don't want to do this. I don't even know how long this goes. This is just awful. Even if I had to stop at 1.732, this This is impossibly painful. Nobody in their right mind would ever want to do this. It's absolutely terrible, right? You just, no. Like, how would I do this? I don't even like dividing by 1-digit numbers. 2-digit numbers are painful. 3-digit numbers, very painful. 4-digit numbers, you give up. And remember, square root 3 doesn't only have 4 digits. It just keeps going and going and going. So instead, what we usually do is we say 10 over root 3 is equal to, now that's equal to multiply both the top and the bottom by root 3, because that's multiplying by 1, right? Root 3 over root 3 is 1. And now that is 10 root 3 over 3. So now this is a little bit more pleasant. What is that? 10 root 3 over 3 if I want to approximate it. So what I'm saying is, if I'm supposed to approximate with this division, I'm too lazy to even start. It's just, no, I don't want to start. There's 4 digits over here to divide by. But watch me approximate this. 10 root 3 over 3. Oh, well, root 3 is 1.732. So this is approximately 17.32 divided by 3. Is this doable? This is so doable. 3 times 5 is 15. I might make a mistake though. I always make mistakes. So in that sense, it's not totally doable, but 3 times 7 is 21, 2, and it's another 7. 21. Yeah, okay, so there's a remainder of 1. But I say that the answer is like around 5.77. That wasn't so bad at all. Imagine if you had to do that thing and get 5.77. Ugh, it just wouldn't work. But so this is just showing you, I'm actually showing you why rationalizing the denominator exists. Oh, that's what we just did. This is called rationalizing the denominator. The reason why rationalizing the denominator was invented is because maybe a long time ago people didn't have these calculators that they could use all the time. And so it was much easier to go and figure out what something is by doing this. Dividing by 3 is painful, but okay. As opposed to doing this, where you try to divide by a number that goes on forever. Okay, so now hopefully you understand why some people want the answers in these weird looking ways. And that's apparently the answer to this question. So that wasn't so bad. More questions. I saw that somebody said, yes, this is also 3.33333 times root 3. You could also think of it that way. The only problem is that multiplying like 3.33333 where there's lots of 3's by 1.732 and like that is also painful. So here I just happened to notice that 10 root 3, well, we were lucky. 10 root 3 is nice. Okay, more questions. And Joe, do you pour the milk or the cereal first in your bowl? I can give you an answer. The answer is I pour the cereal first. But here's why. It's because I guess I care that I know approximately how much I'm eating. I like to know how much I'm eating. And so if I pour the cereal in first, it's very clear how much cereal is in the bowl. And then I pour the milk in, and then it's also very clear how much milk there is in the bowl. Right? But I've noticed from experience that if you pour the milk in first, and then you start pouring in cereal, you're like, how much cereal have I poured in? And then there's also another problem. The other problem is if I pour the cereal out of a bag, as you know from this live stream, I make mistakes. And sometimes when you pour cereal out of a bag, has anyone ever made the mistake before where you tilt the bag and nothing's coming out, so you're like, shake it a bit more, and then you tilt it some more and you shake it a bit more, and then suddenly you hear this like this, like the cereal all comes out of the box. Like, because, it was stuck and you jammed it, jiggle, and suddenly, like, all the cereal comes out. Has anyone else ever experienced this before? I see that some people have experienced this before, too. If you do that and there's milk in the bowl already, it's no good. Then the cereal gets soggy, and then you gotta, like, eat all of it, or it has to dry out. But nobody wants, like, milk that was there from 3 days ago on your cereal. So that's why my advice to you is to pour the cereal first. And this is actually related to a mathematical concept called commutativity. I mean, actually, I do think about the world in this way sometimes. It's like, for math, we know that there's something, there's a key word. There's this word called commutative. And commutative means that you can kind of change the order that you do things in, and you get the same outcome. So one example of commutativity is I can take, this is a neat one. If I want to do commutative, like something that's actually commutative, I could say multiplication is commutative. This is a super cool trick. Does anyone know what is 8% of 25? So this one has a really nice way to do it. 8% of 25 is the same as 8 times 25%, which is the same as 25% of 8, which is obvious. Come on, what's 25% of 8? This is okay. 25% of 8 is obviously 2. Yes, so this is a really, really neat trick. Now, this is not what most people think about with commutative. Most people say commutative means 3 plus 7 equals 7 plus 3. Yes, those are commutative. You can do it in different orders. But here, why is the percent also commutative? It's because if I'm doing multiplication, all percent means is times 0.01. If I write a percent sign, I'm just doing times 0.01. And so what I actually just did here is I said I'm really multiplying three things: 8, 25, and 0.01. And you can multiply 8, 25, and 0.01 in any order that you want, right? Percent is multiplication by 0.01. I didn't want to say it's division, because if I say it's division, you can't really go and say I'll divide in different orders, right? Can I go and say 3 divided by 7 is 7 divided by 3? No, of course not. But if I do multiply by 0.01, yeah, it all just goes around. So commutativity is something like this. But sometimes some things aren't commutative, like subtraction. 2 minus 7, 7 minus 2, they're different. And so I always, like, from this mathematical perspective, I just think about how in the world, some things are commutative and some are not. And in the case of, well, okay, some things are basically commutative and some are basically not. So in the case of pouring milk or cereal first, these are not commutative, because somehow the order in which I pour is going to make some difference. And so anyway, that's how I think of it. And whenever I make that realization, I say, whatever I'm doing in the real world, as soon as I realize that something is not commutative in a very important way, then I have to think, which is the best first thing to do? And then I do that. Okay. I see people are talking about all different kinds of things you can do with toasting bananas. Ooh, cereal and banana expert. Right. Oh, let me tell you something else about toasters. Here is something that you absolutely should not do at home. And I'm not saying this as a joke. Just don't do this at home. This is a terrible thing. So there was one year where I was studying in England for my master's degree. And so I was living in England. I had just finished college. And I was living in a big complex where some of the people, well, I mean, not really living in the complex, but I was living in an area where there were a lot of college students from England. And one day we all got an email saying, please do not dry your socks. Please do not dry your wet socks by putting them into the toaster. Because apparently one of the college students had started a fire by accident because they had this bright idea that, you know, in England it rains a lot. So somehow their socks were wet. Because in England, right, if you know about the weather in England is that it's usually, not usually, but it's often raining. And so it's very easy to get wet socks. And so some brilliant Cambridge undergraduate, you know, this is supposed to be, you know, this is a pretty intelligent students, but some brilliant undergraduate brilliant college students said, I have wet socks. So what you do with wet socks is you put them in the toaster. No, that proves that the action proved that this was a terrible, terrible idea. It actually started a fire. So this was, I'm not actually joking by saying don't do this at home. I'm saying just don't do this at home. Here's a lesson. This is why you don't ever dry your socks in the toaster. It just doesn't work. Okay, great. More questions. And I'm not encouraging anyone to do this. I'm telling you this so that you don't make this mistake sometime later in your life. Okay. Have you ever tried, Anjo asked, have you ever tried baked fries instead of fried ones? Yeah, they're nice too. So, actually in England, that's something that people eat a lot. They're called chips. If you go to England and you order fish and chips, the chips are not like your Doritos or your Pringles, right? The chips are actually like, well, okay, maybe they might be fried, maybe they're not quite baked, but they're not like McDonald's fries. Okay, right, let's keep going. P14, why P14Y3R0N3 says, isn't matrix multiplication not always commutative? You're right. There are some things called matrices. And when you multiply matrices, the multiplication actually matters on what order you do things in. The best way I can explain that is this is something which is not quite matrix multiplication. I don't want to talk about matrices, but I'll talk about geometry. And the way I'll talk about geometry is I'll say, you know, let's suppose I have two kinds of things that I can do. One kind of thing I can do, so I'm going to say I do this to like a drawing. Let's draw a drawing. Oh, I know how to draw a drawing. You draw. Okay, so here I have a smiley face. So I have a smiley face. So now what can I do with this drawing? I have two kinds of things I can do to the drawing. One kind of thing I can do to the drawing is I can turn it 90 degrees. I was going to say counterclockwise because that's how all mathematicians go, but we'll do clockwise, okay? One thing you can do is turn 90 degrees clockwise. And after doing this, the second thing we'll do is we'll shift 1 unit to the right. Okay, so what would that look like? Let's just go ahead and do that. If I did this with the 1 and then the 2, I don't really know what is 1 unit, but you'll get the idea. So I've got this thing. If you turned it 90 degrees clockwise, which is clockwise for you guys? Oh, this is clockwise. Turn it 90 degrees clockwise, then the smile is like over here, but then you shift it 1 unit to the right, and you'll end up getting this face. Something like that. Did that make sense? Like that's what it would mean to first turn 90 degrees clockwise and then shift 1 unit to the right. But now, yeah, so now the question is this the same as shifting and then rotating? Well, you see, the question you asked was about matrices multiplying and being commutative or not. And it turns out that matrix multiplication can be used to encode what we call linear transformations, or in general, I can think of these as transformations. That's not quite the same as matrix multiplication here, because I also have a shift going on. But I'm just giving you some example of how certain transformations that you can do inside the plane, the order matters. Oh wow, you guys even figured out how to draw this. So is it true that there's no emoji for sideways smile? I saw somebody made an emoji for upside down smile. But apparently, hey, we need to invent an emoji. Apparently there's no sideways smile. Oh my gosh, but you know what? That was like the original way people wrote a smiley. Okay, we're not turning 90 degrees clockwise anymore. We're going to turn 90 degrees counterclockwise. And if you do that, now it's a legit smiley. Wait, isn't that the same thing I just drew? I screwed up. So turn it 90 degrees. Yeah, it's the other way around. Something like that. Right? So I think I have that right. Yeah, I think I have that right. So this is like how you actually write a smiley. You write a colon and then a parentheses. So it's the same thing. Okay? So now we're good. But by the way, if you change the order, this is what we mean by commutative or not. If you change the order, what if you do 2 and then 1? If you do 2 and then 1, well, you first shift 1 unit to the right. And now what happens when you do a turn 90 degrees counterclockwise? You do 90 degrees counterclockwise around the origin. So if you first move it over here and then turn 90 degrees counterclockwise around the origin, you end up over there. Does that make sense? So I first shift over to here, my smiley is here, right? And then it turns 90 degrees counterclockwise around the origin and the smiley ends up there. It ends up in a different place. I'm trying to visualize how this looks. 90 degrees counterclockwise. Oh no, sorry. First shift 1 unit to the right. And then 90 degrees counterclockwise. I think it will look like this. Somebody correct me if I'm wrong. But I think what's actually going to happen is that you first move this over here. And then you kind of just turned it up there. And it went there. And if you can see, these two are in different places. And that just shows that it's somehow not commutative. You can't go and say 1 and then 2 is the same as then 2 and then 1. And so this is how the world works. There are many things that aren't commutative. And the more you can recognize which things are and which things aren't commutative, the better you are at figuring out how to eat your breakfast. Okay. Pietro Angelini asks, is the responsibility of being a teacher sometimes overwhelming? Well, yes, because sometimes, I'm thinking about what I want to tell you, and I also am realizing that there are things that I should tell you, make sure not to do at home. So you can see that as I'm telling you certain stories, sometimes I also have to say, oh my gosh, make sure you don't do that. I have to be very careful to make sure that people don't use the stories in the wrong way. But I think in the end, I mean, being a teacher is fun because hopefully you can help some people in some way that they might remember. So I think that's, I guess, yes, in some sense it's overwhelming, and in another sense it's also empowering. Okay. Somebody said a teacher can lose their job if people do bad on a test. Well, in some places that is true. Although I'd like to say, I think that a test alone is not always the best. You shouldn't always say a test is really how you know how good a teacher is. There are actually lots of other things a teacher can teach beyond just what you do on a test. Okay, more questions. We have all these questions here. Now that's interesting. So Alex Xiao says, I don't know if we can do this, by the way. This one might be a brute force question, but I just want to write it down because it's cute. So Alex Xiao says x is a perfect square. But this x is greater than 100,000. That's a pretty big perfect square. And its digits are arranged in ascending order. And of course the question is, what is x? Now, the reason I said this might be brute force is like, good gracious, is there any systematic way to find this? I'm not really sure. And I'm also going to say it's pretty hard, because if you want digits in ascending order, there isn't much room. I mean, I have 6 digits. So it's like, if I go 1, 2, 3, 4, 5, 6, I am in ascending order, and it's almost definitely not a perfect square. And I don't really have much room to be flexible. Like once you go to 9, it's over. So I actually don't know, right? I mean, people are saying you can square random numbers or you can write a program. Here's what I would do. Let me tell you how I would think through this one, right? I would say, well, if I'm going to go and try to make these perfect squares, how many do I have to try? I could go and square random numbers and have as a guess 4, 5, 6, 7, 8, 9, but that's not that easy. I mean, almost definitely your guess will not be right? I mean, the guesses are hard to be right. So here's what I would say. If I was going to try to randomly square numbers, this thing here is about 1,000 squared, right? You see that? This is about 1,000 squared. Well, not about. This is actually, no, it's not. It's not 1,000 squared at all. No, this is approximately, what? What's the square root of 100, of 10? That's like 3. It's about 300 squared, I think. So this is around 300 squared. Okay, so if I wanted to test some numbers, I could try to square numbers like 300 squared, 400 squared, 500 squared, all the way to 1,000 squared. At 1,000 squared, I'd have gotten through all the 6-digit numbers. So if I wanted to check all the way to 1,000 squared, that's going to give you 1 million, which will cover all of the 6-digit numbers. Okay, so by doing 700 checks approximately, I can get through all of these 6-digit numbers. But there's another way to get through all the 6-digit numbers. It's with square roots. I could first say, let's go and find all of the different ways that I could put the numbers in increasing order. And the number of 6-digit numbers that I can write where all the digits are in increasing order is a fun combinatorics problem. Separate question. How many 6-digit numbers are in increasing order, increasing digit order? Now this is nice. It turns out that if I want to make a 6-digit number, I have 9 digits to choose from, because I don't want to put a 0. If they're in increasing order, 0 is not one of them. So I could go and say, hey, out of the bag of digits 1 through 9, let's pick 6 of them. And as soon as you pick 6 of them, put them in order. This is exactly the same as 9, choose 6. Did that make sense to people? If you have digits 1, 2, 3, 4, 5, 6, 7, 8, 9, grab 6, put them in order. Okay, that's a number. So the other way to do this would be to say, let's go through all of these and take the square roots, right? Like I could either square these numbers from 300 to 1,000, or I can square root this many of them. And here I just need to have a way of picking 6 things from 9. But 6 things from 9, picking 6 things from 9 is the same as picking 3 things not to pick from 9. Right? If I have 9 things, I can either pick 6 of them, or I can unpick 3 of them. And so that's 9 choose 3. 9 choose 3 is equal to 9 ways to choose the first one, 8 ways to choose the second one, 7 ways to choose the third one, divided by the number of ways to rearrange those 3 things. That's what we've talked about in a lot of these live streams. Let's go and cancel some stuff. 3, 9 gives a 6. No, it doesn't. It gives a 3. The 2 and the 8 gives a 4. Wow, this is not bad. This is 3 times 4 times 7. 3 times 4 is 12. 12 times 7 is 84. That's not so many things. So I could say, I can go and check all of the 6-digit numbers by only doing 84 checks. And then how can I check all of the 7-digit numbers? In 9 choose 7 ways. I'm just saying, suppose I wanted to solve this problem, I could either go through all of these and do 700 checks to check all of the 6-digit numbers, or I can do 84 checks to do all of the 6-digit numbers. That's amazing. That's really good. And life gets even better from there. Because if I want to then check all the 7-digit numbers, the first method of squaring things will go from like 1,000 squared to like 3,000 squared. I'll have to do like 2,000 checks. Whereas over here, if I want to check all the 7-digit numbers, I just have to do 9 choose 7, which is 9 choose 2, which is 9 times 8 over 2, which is 9 times 4, which is 36. Would you rather check 36 things or check 2,000 things? And the next thing is, okay, how about the 8-digit numbers? Well then, this would be 9 choose 8, which is just 9 choose 1, which is 9. Oh, that's not bad. I would be done in checking 9 things. And what if I had to check the 9-digit numbers? Well, there's only one of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Check if that's a perfect square. So what I'm saying is I could actually be all done by checking less than 200 things, by going through this method of first saying, find the numbers that are with digits arranged in order and take square roots. Or I could do the much more brute force method of squaring things. But I just wanted to show you how these kinds of ways of thinking can save you a lot of work. Only less than 200 things. Samuel Ding is like, oh, come on, what do you mean only less than 200 things? 200 is so painful. Well, it's because on this question, my hunch is that there is no systematic way. In that case, it becomes like, let's write a computer program. And if you want to write a computer program, then the easiest way to do this would actually just be to do, what I just said here. Okay. Okay, more questions. Looking at all of these questions and thinking at the same time. Wow. People are asking all kinds of random questions. And Joe, have you ever had pasta with only shredded cheese? No, I usually like to put the red sauce on. So the answer is no. More questions. Oh, yes. Ellen Wei, here's a fun problem. Let's all do this one real quick. Ellen Wei asked, what happens if you do this horrible 6-digit number divided by this horrible 4-digit number? This is okay. Wait. Oh, Moonwatcher123 said smiley. That's really funny because I saw Moonwatcher and I saw 123 and smiley. But the answer is it's just 123. 1001 is one of my favorite things to divide by, Because, you know, when you multiply a number by 1001, it just shifts the number. So in fact, if I take 123 times 1,000, that's 123,000 plus 123 times 1, which is 123. So this is really fun to go and divide by. And it's great that Moonwatcher123 said smiley right away. And at that point I was like, how did you even know what the question was going to be? But it was your username. Okay, more questions. Broken calculator. This looks like a good way to go and play this. We're getting towards the end, so let's go and try this broken calculator problem. Yes, and this is from Colin Z. I have a broken calculator. I was doing homework on my desk, and I wanted a little more room for my arm. I shoved the calculator off. Broken. That's the problem. And now the numbers say 54 equals 14. 67 equals 19. 92 equals 6. What is 73? Another one of these problems. What could the answer be? At first I see a 5 and a 4 and I say that those are consecutive integers. So that's nice, there's a 1. But I see a 9 and a 2 and that gave me like a 0, 6. So that's not pleasant. What could be going on here? And of course we're looking for not just an answer, we're looking for some reasoning. How might you get these numbers? How might you get these digits? Yesterday we saw some nutty thing where it was like the number of loops. But here we have 14 and we have 19. So it doesn't look quite that nice. It's not like something which we're counting. It's hard to get 19 by counting. The interesting thing is that the 92 gave me a 6. And you know, like the 9 is, it looks like there was a big digit, which was the 9. And when the 9 was a big digit, then there was nothing in front. That's neat. It looks like the 7 is bigger and the 9 is bigger. Oh, but the 2 is here and there's 6. I'm not really sure. So if I look at this, I don't see the pattern. So, we might need some people to help us out. Sometimes with these broken calculator problems, it's that the first digit does something and the second digit does something. But in this case, I don't really see a system to figuring out what's going on with these two digits. The funny thing is to get 6. So from 92 to get a 6, it's like suddenly we got something really small. So if you get something that's very small, you have to think, what is so small about the 9 and the 2? And to me, the 2 is the small thing about this. Because from a 92, it looks like 2 is the smallest. The smallest part of 92. Other things I often would think about are like, is there some prime stuff? Is there some prime factorization? But I don't see anything nice with the 67. And why should that suddenly give a huge number like 19? Yeah, you know what? I'm going to say I don't actually know. I don't see the pattern here. So sometimes with these problems, we also don't quite know, because the person who came up with the problem, we don't quite know what they were thinking. But I'll say I actually don't know the answer to this problem. If anyone here has a... Oh, Colin Z said whoever said 17 is correct. Colin Z asked the problem. So now we know that the answer is 17. So whoever said 17, you're a genius. Now, why is it 17? How is it 17? Let's see. Well, the interesting thing is, because somebody else got it, that means there is a way to do it. And when there is a way to do it, that's actually quite satisfying. So now we know that it's possible. And is it something that you go and get each digit? Were they randomly guessing, asks TempID. It's very hard to randomly guess the right answer. So... you know, like when you go and just like put an answer out, there's like all these different numbers that you could put out there. 5 plus 4 plus 5 is 19. That's true. 6 plus 7, no. You make 24. What is 9 plus 2 plus 9? 9 plus 2 is 11, plus 9 is not 17. So that doesn't seem like it works. Oh, but 9 plus 2 is 11 plus 6 is 17. That is true. But 6 plus 7, how would you get a 6 out of it? So I don't see that. 6 plus 7 plus 6 is 19. Right. 5 plus 4 plus 5 is 14. That's right. 7 plus 3 plus 7 is 17. Oh, that's right. 9 plus 2 plus 9 is not 6. Okay, I'm already seeing that people have something, right? If we did something like 5 plus 4 plus 5, that's 14. You guys are pretty sharp. 6 plus 7 plus 6, yes, that's 19. But what's 9 plus 2 plus 9? That's 20. So I don't exactly see how you get 6 out of this, although 7 plus 3 plus 7 is 17. So then the question is, how is 92 equal to 6? 9 plus 2 plus 9. We don't quite know what happened with the 9 plus 2 plus 9 because that gave you 20, not 6. So I don't quite know. I'm a little curious. Colin Z, if you don't mind telling everybody, how do you go about and get 17 here? Because we managed to find a pattern that works for all except for this one. So we're a little bit curious how this thing went. Let's see if Colin Z can tell us, and then we can finish up. Well, if Colin Z doesn't put it in, well, we'll basically say that this was interesting. I mean, it's interesting whenever there's like different people who come to the same answer. One of them is the one who asked the question, and one of them is actually somebody who answered the question. But we don't completely understand why. 9 plus 92 plus 20 92 equals 20. Please see. Oh, so there was a typo. Is that right? Oh, well, in that case, if 92 equals 20, that solves the whole problem. So if 92 equals 20, it was a typo. And in that case, we're done. So in that case, you guys nailed it because it's just 9 plus 2 plus 9. And what this shows is that the power of the crowd who's watching this live stream is incredible. I mean, I myself didn't quite see what to do with this for quite a long time. And I guess it just shows if you go and find a whole bunch of people to join and think about math every single day for a while, then they kind of figure a lot of things out. Well, crowd power, that's amazing. And actually, I am very motivated by crowd power. That's why a lot of the things that I engage in the world are all based on crowd power. Well, thank you to everybody for joining the live stream today. Thank you for helping to solve all of these problems and also to ask some interesting questions. We'll be back tomorrow. And what will we talk about? Well, I don't know. We'll talk about whatever you guys ask. See you then. Bye-bye.